Welcome to section 5.1. We're talking about trig identities today. We're going to start off with the chapter 4 trig identities that we learned. And again, these are all of the ones that we expect that you know as of chapter 4, and then we're going to give you more today. So let's start with the first type, which is a reciprocal identity. I'm going to start with the fact that the sine of an angle is 1 over cosecant of an angle. And I'm going to go the other way as well. The cosecant of an angle is 1 over the sine of an angle. The second group, the cosine of an angle, is 1 over the secant. And the secant of an angle is the reciprocal of the cosine. And the last type, the tangent of an angle is the reciprocal of a cotangent. And the cotangent of an angle is the reciprocal of a tangent. Now, 4, 5, and 6 are probably the ones we use the most often, but we want to keep in mind that you can write each of the original sine, cosine, tangent trig functions as a reciprocal if you'd like. The second group is the quotient identities, and we use these most of the time for our unit circle work. The first one was that the tangent is the sine over the cosine. And again, we use this to evaluate exact trig values on our unit circle. For example, the tangent of 30, the tangent of 60, things like that. We also did the cotangent, which is, since it's the reciprocal of the tangent, you take the reciprocal cosine over sine. And again, these are the ones we've used the most often. The Pythagorean identities, we gave you 2 of them last chapter. This chapter, you need to know all 3. The first one is that the sine squared plus cosine squared equals 1. And that's the one we use the most often. And we'll use the most often in this chapter as well. The second one, now you need to know this. 1 plus tangent squared equals secant squared. And the third one, 1 plus cotangent squared equals cosecant squared. Okay, so these are the ones from chapter 4 that we expect that you know. Again, number 2 and 3 for Pythagorean identities we gave you last chapter. We won't this chapter. Now the rest of this first page is all more identities that we need to know in order to be able to do the back side. So I'm going to keep moving on. And I'm going to try and give you, I'm going to slide this up. I'm going to try and give you pictures so that you kind of see where it's coming from. This idea of a co-function identity, what I'm going to do is I'm going to draw only the first quadrant of the unit circle, and I'm going to kind of label this a little bit. I know here's 0 degrees and 90 degrees. Halfway is 45, so here's 30, and here's 60. And I'm going to actually write the exact trig values in there as well. This is square root of 3 over 2, 1/2. Square root of 2 over 2, square root of 2 over 2, and 1/2 square root of 3 over 2. And the reason I do this is because these are going to help us with the idea of what a co-function identity is. And the co-function identity we use in terms of actually radians. So let me put 90 as the same thing as pi over 2, and that's important. Co-function means it has to do with complementary angles, and we know that complementary angles add up to 90 degrees or pi over 2. So that's kind of the idea of what's going on. So the first co-function identity they give you is the sine of pi over 2 minus an angle is the same thing as the cosine of that angle. Let me give you an example. The sine of pi over 2 minus, let's do 30 degrees, so pi over 6. So this is saying 90 minus 30 is the same thing as the cosine at pi over 6, or 30 degrees. Well, now take a look. The 90 minus 30 is 60. So the cosine at 60 is 1/2, which is this, the sine of 60 is the square root of 3 over 2, which is the same thing as the cosine of 30. And what they're saying is basically if the angles are complementary angles, then the sine of one of those angles is equal to the cosine of the other. And that's what they're saying. And so I like looking at it in terms of the exact trig values. It works the same way in the other direction. The cosine of pi over 2 minus an angle is the sine of my angle. And you can go the same way. Cosine of 30 is the same thing. Let me try again. Cosine of sine of 60 is the same thing as the cosine of 30. And that's the idea that as we go through, we're kind of looking at. Tangent is slightly different. The tangent of pi over 2 minus an angle is the same thing as the cotangent of that angle. And it works vice versa. Cotangent of pi over 2 minus the angle equals the tangent of that angle. And again, these are what you're going to want to know, and it's the fact that these complementary angles have equal trig values, and that's the idea of this co means complementary. The last one, the cosecant of pi over 2 minus an angle is the secant of an angle, and that works because if you have sine and cosine, their reciprocals will also work. Let me go backwards. The secant of pi over 2 minus an angle equals the cosecant of that angle. Okay, so please keep in mind, if we tell you co-function, it has to deal with complementary angles. Co-complementary, that's what you got to kind of keep in mind. The third type, we've actually discussed in chapters 1 and 2 before. We've looked at the idea of proving that a function is even or odd. And so I want to draw this circle, and I'm going to relate exact trig values, but I want to go back to definitions again. If two functions are even, then we say f of negative x will get you the original back. So if I put in a negative, I should get the original out. If it's odd, we said f of negative x equals negative f of x. Let's see if I can get this right in. So what it says then is if I put in a negative, I get the opposite out. And so this is the idea, and we're going to show you this idea in the trig version of it as well. But I want to kind of keep this in mind. So here we go. Let's start with sine. The sine of a negative angle is the same thing as the negative sine of an angle. And I'm going to use 45s because I think 45s are the easiest. So this has trig values of the square root of 2 over 2, square root of 2 over 2. And down here is the square root of 2 over 2, negative square root of 2 over 2. Now, let's take a look at this. If I take the sine of negative 45, okay, so the sine of negative 45, how does that relate to the sine of positive 45? Well, negative 45 sine value is a negative square root of 2 over 2, where the sine of 45 is positive, so I get the opposite value out. And that's what they're saying in this case. The second one is the cosine. The cosine of a negative angle gets you the same thing as the cosine of the original angle. And I'm going to go 45s again. If I put the sine of, the cosine, let me erase this. If I put in the cosine of negative 45, it gives me the same thing as the cosine of regular 45. And if you look, these cosine values are identical. So this is the idea. So, okay, what is, you know what, I'll discuss even and odd at the end. Let's do tangent. The tangent of a negative angle is the same thing as the negative tangent of the angle. Again, sine over cosine at negative 45 would be negative 1, where at positive 45 would be positive 1. So it's the negative of my original. Cosecant of a negative angle. Now this is the reciprocal of a sine, so it will work the same way. Is negative cosecant of my angle. Okay, and again, these two are tied together. The secant of a negative angle is the same thing as the secant of a positive angle. And again, these two are tied together because they're reciprocal functions. And my last one, the cotangent of a negative angle, let me start again. The cotangent of a negative angle is the same thing as a negative cotangent of the angle. And again, they're reciprocal functions, so they should match. Okay, so what does that mean in terms of even and odd? What that means is cosine and secant are even functions, and the rest of these are all odd functions. Okay, because when you put in a negative, you get out the opposite, where secant and cosine, when you put in the negative, you get out the original. And so again, I want you to remember these. These again were like chapters 1 and 2. So kind of keep that in mind that this is something we still need to remember. We're now just looking at it in terms of the unit circle. Okay, so all of this information is now going to help us work with trig identities on the back side. Okay, in the first 4, we're going to ask you to factor trig identities, which we've never done before. And so I'm going to give you some tips as to if it looks like this, here's kind of our idea of what we should do. So take a look at number 1. We give you the sine of x times cosine squared minus the sine of x. Now this is all one term, so you have 2 terms, and I can't normally factor 2 terms unless they have something in common. So I take a look and I say, look, I have a sine in both terms. So I'm going to pull out this sine as my greatest common factor. And so we're going to just take a greatest common factor in terms of the trig function this time. Well, if I take out the sine of x, what's left? I have a cosine squared minus 1. So we look at this and we got to say, okay, is there anything that I can do with that cosine squared minus 1? And what we want to try and use is those trig identities on the front. So flip to the front and say, okay, which one of those identities maybe has something to do with a cosine squared and a 1? And what you'll find out is that sine squared plus cosine squared equals 1. So I have to rearrange this a second. If I want it to be cosine squared minus 1, then I move the 1 over here, and I move the sine to the right by making it negative. So this part right here is actually the negative sine of x, sine squared of x. And if I multiply that by the sine of x, I get negative sine cubed of x. Because I have 1 here and 2 more here, that gets me sine cubed. Your goal in any of these, truthfully, is to be able to look at this and say, can I simplify this down as far as I can? If possible, 1 trig value. If not, then that's okay. But our goal is to end up getting to 1 trig value at the end. In number 2, you see secant squared minus 1. I'm going to write it like this for a second. I have a something squared, so something squared minus 1. And I'm going to ask you, okay, can you factor this? Well, sure, this is a difference of 2 squares. And normally we'd say this is x and x, and 1 and negative 1. Well, it works the same way. Here, instead of x and x, I have a secant and a secant, and then I have 1 and negative 1. So my factoring is the secant of x plus 1, and the secant of x minus 1. Now, we're going to be doing a lot of trig values, but keeping the x in there is important because eventually we're going to have to solve for x. So you need the x's in there. So we've just factored a difference of 2 squares, looking at it in trig form. Number 3, I'm again going to kind of write it a little differently. I have 4 times something squared. So 4 times something squared plus something minus 3. And if I put it in terms of the x's instead of the tangent, I think then you'll be better prepared to factor this. Now, some of you will use the snip method where you make a table A times C adds to B. For me, I'm going to look at, okay, how is it possible to get a 1 in the middle? Well, I know that 4x is 4x and x, or 2x and 2x. Negative 3 is negative 1 and 3, or negative 3 and 1. And I'm just going to kind of play around with this a second. I know that if I look at a negative 4 and a positive 3, I get a negative 1. So I think I'm going to go the other way. A positive 4 and a negative 3 gets me a positive 1. So I know that my factors, I'm going to be using these 2. So I'm going to write it in the x form first, and then I'll write it as the tangent. 4x and an x, and I need it to be a negative 3. I can't put the negative 3 out here, or I'll multiply to get negative 12. So negative 3, positive 1. This is it in terms of x form. You would get the same thing if you used the snip method, but let's write it as tangent. 4 times the tangent of x minus 3 times the tangent of x plus 1. And I'm okay if you write it in the x form first, but your answer at the end has to go back to the trig function we're working with. So I'm trying to show you, okay, if you look at this and you say, I don't even know, let's go back to the x squared form, because then I think you can factor from there. So the third type is a basic factoring where a is bigger. We have an a value in front. We have a 4, and a lot of times we use the snip method. The fourth one is a similar idea, but you will notice in number 3 we had a tangent squared and a tangent, and these two trig values matched. In this case, take a look, they're different. And so we have to find a way to replace this so that we can have all of the trig values be the same. Well, I can't touch a single trig value, but I do have identities that can help me with the squared. And the one that has cosecant squared is 1 plus cotangent squared equals cosecant squared. Sorry. So what I'm going to do is I'm going to put this in for the cosecant squared. 1 plus cotangent squared minus a cotangent minus 3. Now let's combine our like terms. So I have cotangent squared minus a cotangent minus 2. And again, if you want, perfectly fine to say x squared minus an x minus 2, and then I know this factors to x and x, negative 2 and 1. So I have an x minus 2 and an x plus 1, but I'm going to write it in cotangents right away. Cotangent of x minus 2, cotangent of x plus 1. And the reason we point this one out again is because you started with two different trig values. You can only replace the squared term. Okay, so kind of keep that in mind. The only thing that you can replace is that squared term. And we will make sure that no matter what, that squared term can be replaced. And so this is the first idea of factoring as we go through. And factoring is probably going to be the easiest because you can put it in an x form and you kind of know then the basic ideas of factoring. We're going to move on to the simplify, and the simplify gets a little bit more difficult just because we're not used to working with trig functions. So let me slide this. Let's do this. I want to look at the first one, and again, my goal in number 5 is to be able to get it down to one trig value if possible. If not, the only stipulation is don't leave your answer as a fraction. Okay? Now you'll notice there's nothing in common here. So what I'm going to try and do is make sure all of my trig values are either in terms of sines and cosines. Well, this is already a sine. This is already a cosine, but I know that cotangent is cosine over sine. And I'm going to make this a single fraction, and then we're going to add two things together. So I have the sine of x over, I'm just going to put 1 for a second, plus cosine squared over sine. Now if I want to make a common denominator, I'm going to multiply this fraction by sine on top and bottom. And so what I'm going to do is I'm going to say, okay, if I add one more sine to the top, I get sine squared, and then I'd get a sine x on the bottom. Now if you need one more step in the middle, that's fine too. But you'll notice now that I have a common denominator, I can add them together. Well, sine squared plus cosine squared, light bulb should be going off in your head. That's 1, according to our Pythagorean identity, over the sine of x, but we don't leave our answer as a fraction, and we can say this is the cosecant of x. Okay, so first we wrote everything in sines and cosines, then we made a common denominator, we added things together, and then wrote our reciprocal function. In number 6, the difference is it's already two fractions, so I need a common denominator. So we multiply the first fraction by 1 plus the cosine. We multiply the second fraction by the sine. Okay? In the numerator here then, I get sine squared plus, over here I'm going to distribute, so the cosine plus cosine squared all over, and I'm going to leave this in this factored form. My hopes is, again, if I intermix them, then I have sines times cosines. We'll just leave it and see if things work out. Now taking a look at this, you should be able to see on top you have a sine squared plus cosine squared. And sine squared plus cosine squared is 1. And then I still have a cosine in the numerator. Denominator, I have 1 plus a cosine times a sine. And again, I hope you're thinking, oh, I see something. Because if you look, this is 1 whole factor of a 1 plus cosine, which cancels with a 1 plus cosine in the denominator. So in the numerator, I have 1 over sine, which again, we don't leave as a fraction. We can write this as the cosecant. So we did a common denominator. We looked for that that Pythagorean identity, and that's the one you're going to use the most often. And then once we had that Pythagorean identity, then we just simplified our way through. Okay? 7's a little different in the fact that I don't have another fraction to add it to, and I can't just divide things because I have a plus or minus in my denominator. And so I want you to think of it in terms of this. If I gave you 1 plus the square root of x, we asked you to simplify. You can't have a square root in the denominator, so you'd multiply by the conjugate. Same idea here. We're going to multiply by this conjugate of 1 minus the sine of x on top and bottom. In the top, you just have 1 minus the sine of x. In the denominator, 1 times 1 is 1. Now, I can do the outside and the inside, but we know they should just cancel because they're conjugates. Sine times negative sine is negative sine squared. Now, again, anytime you see a squared, you should start thinking about the Pythagorean identities. And if I look at the Pythagorean identity that has a 1 and a sine squared, I know that 1 is sine squared plus cosine squared. So if I subtract a sine squared, what's left? Well, a cosine squared. So this ends up having 1 minus the sine of x all over cosine squared. And we said we can't leave our answer as a fraction. This is the trickier part of it, is simplifying it the way we need to. So here's what I'm going to do. I'm going to take 1 divided by the cosine squared. So 1 over cosine squared minus, and I'm going to divide it this way, sine over cosine squared. Well, 1 over cosine squared is easy enough. That's secant squared. Okay, let me get rid of that extra little line I somehow put in there. So you have 1 minus secant squared. Minus, now here, if I look at this, I can kind of see sine over cosine would give me a tangent, but I only need 1 cosine. So this, what I'm going to do is I'm going to break it up, and I'm going to put 1 sine over a cosine, but I have left an additional cosine in the denominator, because that gets me cosine squared. So if I look, I know this is a tangent, and this is a secant. So I end up getting, and I'm going to have to just write it here, secant squared minus 1 tangent times a secant. Now, you could try and simplify and factor this out. The point is, and I'll show you in class, it's not worth trying to factor that any farther because it won't help you. Okay, so in this case, just leave it there. But that's the idea in number 7. Let me change colors so we can see the difference in number 8. Number 8, we add the logs with it as well, and we know that the addition of a log means multiply their inner parts. So the natural log, and we're taking cosine times a tangent. And our goal is to simplify this inside. Well, I know that the tangent is the sine over the cosine. And if I look and I make these each a fraction, my cosines will end up canceling. So I have the natural log of the sine of x. Now I'm going to make one change here, because what do we know about logs? I cannot take the log of a negative number, right? So we need to modify this just slightly. We take the natural log of the absolute value of the sine of x. And again, it's all because we cannot take a negative log. So keep that in mind. Whenever you're dealing with these trig things and in logs, it's okay to just add that absolute value in. It's one of the rules that we're actually allowed to do, but we have to do it so that our log isn't negative. That's it for section 5.1. Please know 5.1 is going to be a struggle. What I want you to do, though, is attempt every single question and give it a shot. If we're way off base, it's completely fine, but it gets us thinking in a completely different way than we have before. So give each question a shot.